So in section 2.6, we bring several of the concepts we've talked about so far in chapter 2 together. There technically is one more section in chapter 2, but we are not going to cover it. It's a much more theoretical definition for limits, and it's something that's covered in a much more advanced class called analysis. So 2.6 is our last section for chapter 2, and then we're going to start getting ready for our test. So in 2.6, which is a section about continuity, we're going to start looking at the link between function values and limits. So we've said that function values, which are the points on a graph, are not necessarily the same thing as limits. They can be, but they don't have to be. We don't necessarily have to have a point on a graph in order to have a limit. But if they are the same, then that is something special. We would say that our graph is continuous, that we have continuity. So we start with just a basic definition for continuity, and that's continuity at a single point. And once we understand continuity at a single point, we can extend it out and say, well, how do we know if an entire function is continuous, or the function is continuous on an entire interval of points? So this is just a definition, but after we write the definition, we're going to break it down into pieces, and we're going to have some criteria that we can check. So for right now, this is just a basic definition. So a function f is continuous at x equals a, so just at a single point a, if the limit as x approaches a for this function is equal to f of a. So the answer we would get for the limit is exactly the same as the functional value. The shortcut of what this definition is telling us is that we can do the limit by direct substitution. If we can evaluate this limit with direct substitution without having to apply any of the tricks that we've learned, we don't have to fix any 0 over 0 indeterminate forms. We don't get any number over 0 that turns into infinities. Nothing crazy. We can just do the limit by plugging the number in. That means that our function is continuous there. So one of our most basic strategy for calculating a limit is, well, just take your value and try to plug it in and see if you get a number. If that works, that's because our function is continuous at that value. We have a point at that value. So if you can find the limit using direct substitution, that means that your function was continuous at that point. So this definition actually breaks down into several pieces. There are several things that have to be happening in order for this definition to be true. So we actually break this down a little bit further, and we have some criteria for continuity. And this is going to allow us to pinpoint exactly why something is not continuous, because we can say exactly which criteria fails or which one doesn't hold. So even though we only have this one definition, there are several things that have to be true in that definition. The very first thing is that f of a must exist. There must be a point on the graph. We can't have a hole. We've been doing limits throughout this chapter where there were holes in the graph, and we said holes are not a problem for limits. Well, now in section 2.6, when we start dealing with continuity, we can't have holes. There has to be an actual point on the graph. So f of a, which is just a fancy way to say a y value, f of a must exist, which graphically means there's no hole. The second thing is the limit must exist. The limit as x approaches a for f of x must exist. And again, we've seen some problems this chapter where the limit did not exist. So we had some piecewise functions where the left and the right did not meet up. So that was because there was a gap in the graph. So we are not allowed to have gaps in the graph. We must be able to calculate that limit. So there has to be an actual point on the graph. We have to be able to calculate the limit. And then the third criteria is that these two values must be equal. Since we can calculate both of them, they must equal out to be the same thing. Since they're both dealing with x equals a, they must actually equal the same y value. And what this looks like on a graph is we're not going to have any jumps. And I've got a graph I can show you that's got all three of these on there. And I can show you exactly what the holes look like and what the gaps look like and what the jumps look like. So we can pinpoint all three of these different little anomalies that would create discontinuities in our function. So all three of these are actually in this definition. We just broke it down into smaller pieces. So we have to have a function value, we have to be able to do the limit, and they must equal the same thing. Sometimes we have a function value, sometimes we have a limit, but they're equal to two different things. And that would not help us with continuity. So I'm not going to draw this graph out. What I'm going to do here is I'm just going to paste it. Oops, did not want to do that. Did not want to do that either. Let me see where I had it. I think I can just right click. Yes. Yes. Oh wow, it came out big. I didn't mean for it to come out that big, but that's okay. All right, so this graph has all of the different things I was just talking about. And we're going to write all over this guy and point all of them out. So we have three criteria. The first criteria is that we have a functional value. Second criteria is that we can do the limit. Third criteria is that they equal the same thing. So this is the graph of f of x, and we're going to go along this graph and we're going to point out which of the different criteria are not met. So if we start tracing along this graph, everything is fine. But when we get to x equals -2, we have a hole in the graph. We can do the limit at holes. That's perfectly fine. What we don't have at a hole is a functional value. There technically is no point there. There's no y coordinate. So at x equals -2, and I'm going to do this in a different color. Let me see if I can do it underneath. Yeah. At x equals -2, we have a criteria number 1 is not met. We don't have a functional value. F of -2 does not exist because we have a hole. Our first criteria was that f of a must exist. We can't have any holes. The easy way from a graph to tell if it's continuous is if you can draw the entire graph without ever lifting your pencil. So if at any point when you're drawing, if you have to lift your pencil to move it to another spot, that means you have gotten to a point where there's a discontinuity. So when we get to -2, we have to lift our pencil to jump across -2 to restart our graph. So that means there's a discontinuity at -2. So we jumped across -2, there's a problem there, and we keep drawing. Now this is a continuous piece because I can draw the whole thing without lifting my pencil. But once I get to, it looks like x equals -1/2, I've got another hole. But notice that there is a point. It's just at a different spot. So this is a jump. There is a point that has an x value of 1/2, but it's not where the limit is indicating it should be. So this is the number 3 criteria, where our limit does not equal our function value. It looks like the limit is saying it should be up here at 3.5, but the actual function value is down at 1. So there is a limit, there is a point, but they're at 2 different spots. So at x equals -1/2, we are not meeting criteria number 3. Our limit does not equal our function value. The limit as x approaches -1/2 does not equal f of -1/2. They're 2 different things. And that is a jump. As we're tracing, we've got to jump away to fill in the circle, and then we jump back to keep drawing the graph. All right, and then we'll jump back and keep tracing, and we get to 3, and then we'll have to pick up our pencil and move it in order to keep tracing. That means there's a discontinuity here at x equals 0. So at x equals 0, there is a function value because we have a colored in circle. The problem is we can't do the limit there because from the left it looks like it's going to 3. From the right it looks like it's going to 5. So at x equals 0, the limit does not exist. So we are not meeting criteria number 2. The limit as x approaches 0 for f of x does not exist. And if you look at the graph, there's a big old gap in our graph there. This big old gap here. All right, and we will keep on tracing, nice and continuous. And then there's another big old gap here at x equals 1. So again, a spot where the limit doesn't exist. From the left, it's approaching 4. From the right, it's approaching y equals 0. And that's happening at x equals 1. So another number 2 criteria that we're failing. The limit as x approaches 1 does not exist. It's doing 2 different things from the right and the left, and it's creating a big old gap in our graph. And then we'll keep on tracing. and we'll have to pick up our pencil and jump across our asymptote in order to keep drawing. There's a big old gap at x equals 3. The limit does not exist there because one side's going up, the other side's going down. Anytime the graph is going off to positive or negative infinity, technically the limit does not exist. So at x equals 3, another number 2 criteria is not being met. The limit as x approaches 3 for f of x does not exist. It's a gap. Technically, it's a vertical asymptote. And then we'll keep tracing. And we'll have to pick our pencil up at x equals 5. We can do the limit because the left and the right sides meet. So that's okay. The limit exists. What does not exist is there's no point there. It's an open circle. So when there's no point, there's no functional value. So f of 5 does not exist. That was our first criteria. So we would say there's a discontinuity at x equals 5. And that was our number, the number 1 criteria. So x equals 5, we're not meeting criteria number 1. F of 5 does not exist, which was a hole. So there was a lot of them. 1, 2, 3, 4, 5. There were 6 places where this graph had a discontinuity. We had a hole here at -2. We had a jump at -1/2, and that's because we jumped down here away from where our actual graph was. We had this big old gap in between the pieces of our graph at 0. We had another big old gap between our pieces at 1. We had this vertical asymptote at 3, which is considered a gap again. And then we had a hole at 5. So 1, 2, 3, 4, 5, 6. Yep, 6 different continuities. And that we were able to find at least one of each of the different types. So most functions that we deal with, if they're given to us in function notation, they're going to be continuous, especially polynomials. You may remember from algebra class that polynomials are continuous functions. From negative infinity to positive infinity. They have no holes in them, they've got no gaps in them, they've got no jumps in them. Usually when we have to restrict the domain of a function, it's because they have a discontinuity. So if you think back to algebra class, of the types of functions that we had to restrict the domain for, rational functions, we had to restrict the domain because we didn't ever want to divide by 0. Or radical functions, we had to restrict the domain because we didn't ever want to take the square root of a negative number. So continuity is very similar to finding domain. Anywhere we have a discontinuity, it's very similar to domain. They're not exactly the same thing because we could still have a filled-in spot, which means it's part of the domain. But the holes and the gaps, those vertical asymptotes and those holes, those would not be part of our domain. So anything we would throw out of the domain of our function, those would be discontinuities. But one type of function that we know we can always count on to always be continuous are polynomials. But another type of function that we come across that usually gives us trouble are piecewise functions. And usually we only have trouble with them where we're trying to get them to connect, where we switch from one function to the next function. So we should check really quick to make sure the individual functions are continuous functions. So we're going to check the individual functions for continuity. And for the most part, we'll be working with polynomials, so they'll be fine. But more importantly, also what we need to check, if we want our piecewise function to be continuous, we need our two separate pieces to connect in the middle. If you look back up at this graph we just messed around with, very often piecewise functions don't connect. Where one piece ends and the other piece starts, if they don't connect, there's a big old gap in the graph. And if we want the function to be continuous, we need those two pieces to connect. So we also need to check and see what's happening when we switch from one piece of the function to the other piece. So we want to know, is f of x continuous? And f of x is going to be a piecewise function. So let's say that f of x is x squared minus 2x for all the x values less than or equal to 1. And then it's 3x plus 5 for all the x values greater than 1. So individually, these two functions are perfectly fine. They're both polynomials. X squared minus 2x is a parabola. It's a second degree polynomial. It's continuous from negative infinity to positive infinity. It won't have any holes, any gaps, any jumps. 3x plus 5 is a first degree polynomial. It also is not going to have any holes, any gaps, any jumps. So individually, both of these functions are continuous. So really all we need to check for is what is happening at x equals 1. Are these two guys connecting? Well, they connect if they meet up at the same point. And a point has an x value and a y value. Well, we're told the x value. The x value is 1. What we want to find out is if their y values match up. If the y values don't match up, then there's a big old gap in the graph. If the y values do match up, then the two pieces are connecting. So all we need to do is take 1 and plug it in to each of these guys and see what y coordinate they're at. If they match, then they're connecting. If they don't match, then they are not connecting, and there's a big old gap in the graph, and it's not continuous. So x squared minus 2x at x equals 1. We want to know what's going on. And then 3x plus 5 at x equals 1. We want to know what's going on. So 1 squared minus 2 times 1 is going to be negative 1. So our parabola is down at a y value of negative 1. And if we want to, we can write that at a point, as a point. It's down at 1, negative 1. Our line, 3 times 1 plus 5, that guy's at 8. So our line is at the point 1, 8. So when we switch at x equals 1 from the parabola to the line, we are jumping from 1, negative 1 up to 1/8. And there is a giant gap in the graph. These two guys are not connecting. This function is not continuous. We need those y values to be the same. If they're the same, that means these two pieces connect. So those are not the same. Another thing that we can do is we can figure out how to make them connect. We can solve for a so that f of x will be continuous. So let's say we've got f of x equals x squared plus 3x minus 5 for x less than or equal to 2. And then we've got negative 2x plus a for x greater than 2. So again, we've got a parabola and a line for our piecewise function. A parabola is always continuous. That's a second-degree polynomial. A line is always continuous. That's a first-degree polynomial. What we don't know right now is what the y-intercept of this line is. And we've got the option to adjust it, which is technically sliding this line up and down the y-axis so that it's in the correct spot to make this function continuous. We're going to do the exact same thing in this problem that we did in the last problem. I know that it'll be continuous if my y-coordinates match up. I need the points overall to match up. I need this to be 2, something, 2, something, and those somethings need to be exactly the same. So what we're going to do is we're going to plug in 2 and see where the parabola is at, plug in 2 and see where the line is at. Now we're not going to get a number answer for the line because the line has an unknown a in it. But if we know we want to make this continuous, then we know we want to make those question marks equal. I don't know why I just put a not equals on there. We have to make them equal. So we're going to set them equal to each other and we'll be able to solve for the a to make them equal. So let's see where our parabola is. X squared plus 3x minus 5. We want to know where it is at x equals 2. If we plug 2 in, we get 2 squared plus 3 times 2 minus 5. That's 4 plus 6 minus 5 is 5. So our parabola is at the point 2, 5, which means our line needs to be at the point 2, 5 as well. If we want this function to be continuous, the parabola and the line must connect. So our line, negative 2x plus a at x equals 2. So let's plug in, we know we're not going to get a number answer, but let's plug in what we know and see what we can do. If we plug in x equals 2, we get negative 2 times 2 plus a, which is negative 4 plus a. Well, if I want these graphs to connect to make this function continuous, this value must be the same as this value. That's why the last problem was not continuous, because these guys were not the same. We had to jump from negative 1 to 8, and it made a giant gap in our graph. That's why it was not continuous. If we can make them the same, then it will be continuous. So I want negative 4 plus a to come out to be the same as 5. I want negative 4 plus a to come out to equal 5. So we've got the option to assign the a value to make this true, to make this work. So we can solve for the a that will make this work. So I'm going to say negative 4 plus a equals 5. And we're going to solve that. So add your 4 over. And a has to equal 9. If a equals 9, then this function will be continuous. If a is anything else, then it won't. It will not be continuous, and there will be a giant gap in the graph. So that line needs to be negative 2x plus 9. If it's anything else, we'll have a gap in the graph. So the whole idea is we're already told where we're changing graphs on the x-axis, and to be continuous, we need their y's to be the same. So we can plug in those x's and check on the y's. If the y's match, it's continuous. If they don't match, it's not continuous. And in this case, we can solve to make it continuous. All right, now the last thing I want to talk about really quickly in this section is the intermediate value theorem. We're not really going to do anything with it right now. I just want to introduce it because it's a direct result of this idea of continuity. We're going to use it more in later chapters, but it has to do with continuity, so and it gets introduced in this section. So I just want to introduce you to the idea here real quick. The intermediate value theorem is just an existence theorem. It guarantees us that something in particular exists. It doesn't really tell us how to solve for something, but it's useful that it promises us that something in particular is always going to exist, and it's because of continuity. So what the intermediate value theorem says is suppose f of x is continuous on the interval a to b. So it doesn't necessarily need to be continuous from negative infinity to positive infinity. We could just kind of look at one little section if we want to. And L is a number between f of a and f of b. So those are the y values that go along with the x values in the interval that we're working with. So what the intermediate value theorem promises us, if f of x is a continuous function, is then there exists at least one value c in the interval a to b such that f of c equals L. And I think this looks a lot nicer on a graph. It's a lot easier to understand from a graph. So if you have a y value in between your endpoints, there has to also be a corresponding x value in between your endpoints that goes with it, if it's a continuous function, because we know continuous functions have no holes, jumps, or gaps. So the only way to get through, to get from one endpoint to the other endpoint is to go through all of the possible values in between. That's pretty much what the intermediate value theorem says. It goes through every single value in between. So I want to show you really quickly on a graph, and I think it looks a lot nicer on a graph. It makes more sense on a graph. So let's say this is our f of x. And here's our a, here's our b, If we follow those up and across, then we'll have our f of A and our f of B. So what the intermediate value theorem says is L is a number between f of A and f of B. So we can just pick any random L value in between f of A and f of B. If f of x is a continuous function, we should be able to follow that back to the function and find a point on the function, and then follow that back down to the x-axis, and we should get an x value that's in between A and B. Then there exists at least one value C in the interval A to B. And that's what we just found. If you have a y value in between f of A and f of B, it should correspond to an x value in between A and B. If you're working with a continuous function, that should always be true. If you're not working with a continuous function, then you can have these little jump points that go all over the place. And you can have gaps and you can have holes, and there's no guarantees. But for nice continuous functions, this is always going to be true. And looking at the graph, it seems obvious. Well, duh. And the reason this is true is the only way to get from this point to this point is we have to go through every single value in between. We've got to cover every single value in between x equals A and x equals B, and that's horizontally, and we have to cover every single value between f of A and f of B vertically. If it's a continuous function, we have to go through all of these x values and all of these y values if it's a continuous function. So that's what the intermediate value theorem guarantees us, that in order to go from A to B and f of A to f of B with a continuous function, we are going to cover all of the values in between. So if we need to, we could work backwards and solve for particular values if we want to. And the intermediate value theorem is actually really useful in finding x-intercepts. And we actually use the intermediate value theorem in algebra class to prove that we have intercepts at particular points. Because if we can find a positive y value and a negative y value, then we're guaranteed that there's an x-intercept somewhere in between, because the only way to go from a negative to a positive is you have to go through 0 in between. So you may remember that from algebra class. So we'll come back to this again in a later chapter, but they talk about it briefly here in this section just because it's a direct result of learning about continuity.